Here is the ecsp user's guide for the transmission line model. It's a traveling wave model. There are two different ways how you can model a transmission line. This is a single phase representation. Here you have the source, and here you have then the transmission line. Transmission line in this case is 200 kilometers long. It has 5 segments, and this is the more traditional way how to do it. Here you see the source voltage, the trace of the source voltage of both models. And here you see the voltage and the current at the load. And this is now different between the traditional model and the traveling wave model. Traveling wave model is more precise. For the user's guide, I will focus on the traveling wave model. Each line model is based on 2 wave models. One wave model is for a forward traveling wave, and the other wave model is for a backward traveling wave. Each one of the 2 models is based on an array of segments. The number of segments should always be bigger than 1, so at least 2 segments. And at the beginning and at the end of the traveling wave model, both elements are added together. So you have always the sum of the forward and of the backward moving wave. At each time steps, the values are passed from one segment to the next one. So you see, if the source has a value of 1, for example, the first time step, this value of 1 is put into the first segment. The next time step, it is moved from the first to the second, and so on. So it moves across the array, and the same happens with the backward moving wave. Here you adjust the line parameters. It's double click. Then you have the ohmic resistance per meter. All the values are per meter. So ohmic resistance, then impedance. This is a standard value. You can change it, of course. When you change the impedance value, you will see that the micro, henry and picofarad per meter are automatically adjusted. But you have to push enter. Then the line length, also in meters, so this is 200 kilometers. Speed of light, normally it's 300,000. This is just a percent of speed of light. And then you can also give an initial pre-charged value. So if the line is pre-charged before you start simulation, you put the value here. Then you can also, instead of entering the impedance value of the line, you can also enter the microhenry per meter and picofarad per meter value directly, and then it calculates backwards, calculates the line impedance value. So this is for the line parameters. You can either connect all the 0 points, you can interconnect all the 0 points, or it's enough if you connect the beginning and the end. You can also add a grounding sign, so then the 2 line ends are grounded. At the start and at the end of the value, you connect it the similar way like you connect a resistor. So this is the beginning of the line, this is the end of the line. And when you adapt the number of steps, you also adapt the number of segments automatically. So I reduce the number of steps now to 500, and you will see you are now on 17 instead of 170 segments. These are the segments I have been showing before. So here you need to have at least 2 segments, otherwise the calculation doesn't work right. On the members only side, you have also access to a little bit the simpler version, where you can easily assemble some more complex networks. This is exactly the same line as this one. The only difference is that these 2 grounding points are not shown. They are automatically grounded with a grounding sign, but then you need also to add another element which then has a grounding sign. For example, you may add a voltage source, and you may add a resistor or an impedance or whatever. Let's go for a resistance. Then you need to add a grounding sign, otherwise it will not work. So that's what you need to do. So that would be the correct the application of this one. So it's simpler. You can then just add as many as you want. And there is a third alternative. This is a three-phase circuit, which is exactly the same as this one, but for 3 phases, and it has an additional input needed. This is the so-called phase coupling. So it may well be that the phases couple each other. So if you have 3 phases, one phase will kind of influence the other phase, and the coupling factor, that's what you can input here. Okay, then let's go quickly for a 3-phase setup. This is now the 3-phase line. I have a 3-phase source already, and I close the whole story with a 3-phase resistor. Let's go for a 500 ohm. Let's look at the voltage and at the current here. Here I go for a 100 kilometer line. And let's go for 10 micro ohm per meter. First, no phase coupling. Then I just ground the whole thing with some grounding signs. I should never leave any connection dot open, so I have always to ground it if possible. Then millihenry, let's go for 5. And we have our source, yes, and also this source, the neutral, should be grounded. Does not have to be, works also with that. Let's see what comes out now. You see I have 4 segments now, and this is now what I get in 3-phase. Of course, if I go for a permanent calculation, these initial TRVs will disappear, of course. You see, and here you have the timeline. I can now change and say I want to have a phase coupling. Let's go for, let's say 20%, to go for an extreme case now, just to see what comes out. So I have now a phase coupling. That means the one phase influences the other. I invite you to test it yourself on www.ecsp.ch. This is where you find the simulator. It's very easy.